Hello everyone, my name is Felienne Hermans and I'm the author of the book The Programmer's Brain. And in the Manning API conference, I will talk about how to design an API for people. Because designing an API, you're often thinking about functionality, right? Oh, this feature should be in there. Oh, and I should support this use case. But APIs ultimately are also user interfaces. They're meant for people to use. So in my talk, I'll talk about the cognitive aspects of API design. Hope to see you in August. Bye! Hello everyone, my name is Felienne Hermans and I'm the author of the book The Programmer's Brain. And in this video, I'll talk about a later chapter in my book, chapter 12, that talks about how to design libraries, programming languages, and APIs to create APIs, as you see on the slide, for people. Because if you create an API, very often you're consumed by thinking about functionality, right? You're thinking about, my API should support this feature and it should have this functionality. But of course, ultimately, APIs are also user interfaces. They're meant for people to use, to call. And in thinking of that, you of course have to also think about how will people use this? Will they understand this API? And that is what this video today is about. I'm going to introduce a framework that can be used to assess the usability, the cognitive usability of programming language libraries, but also APIs. The framework that I'm going to be talking about today, which is also covered in my book, is called cognitive dimensions. Cognitive, of course, because they pertain to the cognition of people, how people think about APIs, libraries, programming languages. And why this is called dimensions is because the cognitive dimensions are properties that a programming language can have. Just one example that we'll talk about today is error proneness. So a programming language or an API can be very error prone, or it can be robust against error. So it's a property that a programming language or API can have. But some properties, we'll see examples of this later in the talk, are mutually exclusive. For example, if you make an API less error prone, if you add all sorts of types and tests and assertions and checks, you make it less error prone. However, you might make it also less usable. So you can move something in different dimensions that are related to each other. And this is why the framework is called cognitive dimensions, because these aspects are all different from each other, but also related to each other. And in this talk, very often I will say a programming language can have, because originally the framework was designed to evaluate the usability of programming languages. However, in my book, I generalize a bit and I say, well, this framework that was actually made for programming languages can also very much be used to look at properties of code bases, specifically code bases that are meant as interfaces to other people, for example, an API. So excuse me if I say programming language. Everywhere I say programming language, you can also think API or code base. In the remainder of this talk, I'll simply go over a list of different dimensions. And in the end of the talk, I'll wrap it up with some practical ways in which you can use the framework. So one of the dimensions, the first that we're going to talk about, is called viscosity. So the thickness, so to say, of a framework. And viscosity means resistant to change. How easy or how hard it is to make a certain change. For example, you might be aware of the block-based programming language for kids named Scratch. In Scratch, changing an if statement to an if-else statement is a very cumbersome operation. If you have never seen Scratch before, here it is. So here you see an if statement and an if-else statement. If you want to change the one in the other, you have to drag away the first block and then drag in the second block and take your blocks out and copy or drag them into the new block. So this is lots of work. If you compare that to a textual programming language, in which you could simply, if you already have an if, take your cursor, put it at the end and say else and then the rest, you see that the one, in this case the visual, the block-based language, is harder to change. It takes more effort to change than a textual language. And this is of course also very much true for API calls. right? If suppose you have in your API something also like a condition. Is this a function with the word if, with the name if, and also you have a function called if else, and if you want to change the if, you have to change the if else? Or do you have something like condition, where the first argument is the condition, and then the second one is the if, and the third optional argument is the else branch? See, that's an easier change. It's an easier change to add an argument than to change the name of a function. So if you're designing an API, you can also think of what functions are related to each other. Which function could I potentially transform into another function, and how hard is that change? Because your API users, they're not going to get it right the first time. So it's very likely that first they have a certain call and then they change their call. So that is the property of viscosity. Is it easy to change? Another example where you also see the applicability, the broad applicability of this framework is in Word, in a word processor. If you want to change all headers, if you've properly configured a style, then it shouldn't be so hard. But imagine, I admit I have done this, all your headers are bold, and then you think, oh, I don't want this bold, I want this in blue or something. You have to select all of them and make all of them blue instead of bold. That example of Word is actually an example of how sometimes, if you do a little bit of effort beforehand, viscosity can be lower later on. And so if you, for example, also in making modules or making function, if you've already put stuff into a function, then later on, reuse is easier. Adding something is easier because you already did a little bit of pre-work. So there's this inherent viscosity that the language might have, but there's also the viscosity of the user. The better organized your code base already is, the easier it will be to make changes. So I hope you're now getting a sense of, oh, this is an aspect, it's not really like measuring, right? You're not going to say the viscosity of my API is 7, but it is, you can get a sense of a feeling for, does my API have high or low viscosity? And there are much more dimensions to be discussed. So let's hop over to the next one, visibility. Visibility is how easy is it to view different components? How easy is it to understand what is in my system? For example, in programming languages, again, if you have an object-oriented code base, you might want to see all classes in a project. That isn't so easy, right? There isn't something like it. They exist, but they aren't always commonly used. Something like extract a list of classes from my project. So classes are there, but to see that is not all so easy. So that is an aspect of visibility. This is, of course, also something that can be applicable on API design. For example, is it very easy for your user to see all functions that you expose, or all objects that are possible that you can inherit and override and use? Or given a certain function, is it easy to understand what arguments does this function take? So visibility is something very much related to understandability and readability. How are you helping the user to make sense of what is possible? And this doesn't necessarily need to be in the code base only, right? You can have documentation in which it's very easy to see what is there. If you see, maybe my code base, my library, my API is lacking visibility, you can compensate for that, of course, with better documentation. Another example of a dimension is hidden dependencies, which is very related to visibility, but a little bit precise. Hidden dependencies expresses how easy it is to see what relates to what links are visible or what links are invisible. So at this point, it's time to bring in one of my friends, because I know it's very hard to just listen to people talk all day, right? Even if the talks are really, really engaging, just sitting and listening is just not the best way to learn. If you want to know more about what is the best way to learn, my book, of course, The Programmer's Brain, would be a great resource. Stuff that my book also says is that it's very important to participate actively and to think, to elaborate on what you've just been shown. So here's my friend, the participation pen. whenever the participation panda occurs on the screen, it is your job to do something. So you might grab a pen or a paper or your phone, because I'm going to ask you a question to help you process what you're learning. So the first participation panda question is, can you think of an example of hidden dependencies? So what are aspects in a code base where dependencies might be there, but might be invisible? So I'll give you a little bit of time to think about an example of hidden dependency. Maybe you thought of this. Find everything that calls a certain method. So this is a dependency that exists in a code base. You have a method or a function, and in other places in the code base, this function is being called. That is a dependency that is not typically visible in the code. You can always see where am I calling a method, right? Because you see the name of the method. So you see where the method is called. But if you're in the method, if you're at the method definition, you can't see there where it's being called. Of course, IDEs compensate for this a little bit, right? In many IDEs nowadays, you can right click and you can say, give me all the call locations or all the places, all the dependencies. But from just the source code level, the dependencies are invisible, which is not always what you want. And this might be true also, of course, again, in API design. So internally, you might all have all sorts of methods and objects and classes from the call side, the person, the user of your API. They maybe will not see all of that, depending on whether this is a compiled library or whether you're actually shipping the source code to the user. They might not be able to see all dependencies, which might not always which might not always be what is most comfortable for the readability of the user. So this is also something to think about. In your library that is exposed to the API, what are the dependencies that might matter to the user, and do we help them make sense of those dependencies? Here's yet another dimension, the dimension of role expressiveness, which is a bit vague, and the definition, I will admit, also keeps it a bit vague. Role expressiveness means how clear it is what role entities are playing. So what does that mean? That means if you look at something, a method, a variable, a function, can you see, does it tell you what it is? For example, if you see a variable x, do you see what the type is? What tells you this? It might be a little bit vague. Even so, before I'll give you more concrete examples, let's do one round of participation panda again. So think of an example in a code base where you're looking at a thing, function, method, variable. How does the programming language or the IDE help you understand what the role of the thing is? What is an example of role expressiveness? I'll give you a sec again. Well, I take a sip of water. Okay, I hope you came up with something. So role expressiveness, for example, is colors in Scratch, in the visual language that we just saw, the block-based language. Here you can see that different blocks have different colors. So you can see that the yellow one is like control, a control structure, but the bluish one is like a condition, right? It fits into a condition slot, and the purple one is output. So the colors here are expressing the role of the thing. Hey, this is an expression, this is a command, this is a control structure. But of course, it's not just block-based languages that have role expressiveness. Syntax highlighting is also an example in textual programming languages of role expressiveness. I can look at a string, and typically a string will have a different color than a keyword. So a keyword, just by looking at the color, tells me this word. If it's not the name of a variable, some programming languages might allow a variable with the name if, then if you see an if, you can see by the color, here it is a keyword, and here the word if is embedded in a string, for example, which most programming languages would allow. So you can see here it's a keyword, but here it is a plain text string. To stay more in the realm of API design, examples of role expressiveness are also, for example, named parameters. So if your API exposes parameters that may be named like is common in Python, where instead of saying motor and then 100 for set the power to 100, many programming languages allow something like motor, open bracket, power is 100. So that power is helps you to understand what the meaning is, what the role is of the number that follows next. So it tells you the block as itself, like power, like power is 100, tells you what the role of the 100 is, because it plays the role of setting the power. So that is role expressive. Another dimension. We'll do a few more before we go to the concrete implementation of the framework. Abstraction. Abstraction is the ability to add notation to a programming language very often. So can I make my own something? For example, can I create my own function? Can I create my own object? Can I create my own class? Can I add something that looks like sort of the rest of the programming language? And this is very much a design decision in APIs. So some APIs are like purely functions. They say, here, we have our own objects and methods, and what you can do, user, is you can call things. That's what we give you, and we process everything behind the scenes. That would be a library or API with low abstraction power. The user can't really do anything, can't create new things. Whereas other APIs say, no, rather than exposing functions, what we expose is classes. Here's our class, and you can simply inherit from this class and add your own fields. That would be a design that allows the user for more abstraction, allows the user to create their own little blocks of logic. And both are like have value, right? It isn't, none of these dimensions is really like this is better than the other thing. They all have their pros and cons. Both designs have their own reasons, but the goal of this whole framework is, we'll talk about that a little bit more in the end, is to think about all these things. Because what I've seen with many code bases, programming languages, and APIs is, they start small and it's like, oh, let's just expose this. Oh, we can do this. Oh, you know what users might also need? Oh, that other thing. And then these things like grow out of hand without ever thinking, oh, but what do we want here? Like as a design choice, how should this look like? Do we want to give the user abstraction power? Or do we rather say, no, it's not a good idea. We want to keep all the calculations inside. And then you get this mix of, oh, here's a few functions, but also there's one class that you can use. And that is what is so confusing. So it's really not meant as something that, oh, you should have, your user should have much abstraction power or shouldn't have expression power at all. What matters is that you make an explicit decision about this. Error proneness, then. This is, I think, the most like normal dimension, and also a dimension that we do talk about a lot. Very often, if we talk about the design of programming languages, I myself am a member of the TC39 committee, so I help design JavaScript, and we talk about error proneness a lot. Like with new features, people will say, oh, but if we add this, then no, we call this in our community, this is a foot gun. We say, this is a feature that is easy to shoot yourself in the foot with. So error proneness is a feature, or a dimension, I should say, that people talk about a lot. And it's sort of the definition, of course, is, does the notation prevent mistakes? It is panda time again. Can you think of an example of where a language or a framework helps you to not make errors? What is an example of a language with good, so to say, high defense against errors? Okay, I hope you found a few examples. One example is that in Scratch, you might have seen this from the shapes. Invalid blocks don't fit. They just don't click together. Here you see some blocks that have rectangular side, like the if, but some have triangle sides, like the key, and some have round holes. And they don't fit into each other. So this is a notation that helps you not make mistakes, because you can visually see, oh, this thing, it doesn't go in the other thing. In more traditional textual languages, of course, I think you might have thought about A type system. A type system is typically a thing where we say, well, if a language has types, then this helps you not to make mistakes. Because if you accidentally add one type to another type, a typed language will say, hey, these things don't go together. A C-type language might say, hey, this is an int and this is a string. This cannot be combined, so you get a compile error, while a Python or JavaScript language would be, oh, sure, well, I'll just try to throw it together and we'll see what happens at runtime. Another dimension that is interesting, also specifically in the context of API design, is secondary notation. Secondary notation is where you can add notation to your notation, so to say. You add notation on top of formal syntax. For example, textual languages have comments. So a comment is something that isn't really the formal syntax, even though, of course, it should still be parsed, but the parser ignores it, doesn't do anything with it. White space, new lines, is also an example of secondary notation. We've all seen these very, very long blocks of code, and then you intersperse them with a few lines of white space, and that sort of helps you make sense of it, even though the compiler just eats it up and doesn't look at it at all. And in Scratch, you've seen those blocks. You have the secondary notation that you can put stuff like next to each other. You can put a block here and there, and that can also convey meaning. Earlier, when we talked about role expressiveness, we talked about named parameters. So named parameters are also, in a sense, an example of secondary notation. They do a bit of expressing roles, and they also do a bit of secondary notation. Because for a parser, it really doesn't matter if you put their motor power is 100, or if you put their motor 100, because it knows what the arguments are. It just uses that to match the arguments, but it doesn't change the meaning of what it does. So that is a bit of secondary notation as well. You can debate for a long time when it is secondary notation. Some people say that it's only secondary notation when the named arguments are in order, because then it doesn't change the meaning. And if they're out of order, then the meaning gets changed. So then maybe it's not secondary notation. But what matters is that there are things that you can give to your user that aren't the formal syntax that help the user understand what's going on. Proper naming can also be seen as secondary notation. You can create an API where all the functions are called X and Y and B and Z. It works fine, great, it has the functionality. But giving everything a really good name, of course, helps readability without really changing the meaning of the program in terms of the meaning for the compiler. Closeness of mapping, also very interesting dimension in API design. Closeness of mapping means how close is your language to the domain, like the thing you are doing. An example of this, people that have checked out my book have seen that we have quite some examples in a programming language called APL, a programming language. And that's a programming language that's entirely based on vector calculus. It is very, very hard to understand, but if you understand vector calculus, then APL is actually pretty easy to understand because the core structure of APL are vectors. Textual languages typically don't really have good closeness of mapping, because in Java you can create an app for finance and banking and insurance and shipping. So there isn't anything about Java or Python that make it very suitable for finance. However, APIs, of course, are sometimes very close to the domain. And this really matters because in Java, you're not going to have set interest rate. But in an API, you might expose all sorts of functions that are very, very close to the domain. If your API is more, if your library is more a domain-based library than something for, let's say, databases, which is still very far away from domains. And of course, this closeness of mapping is something that really, really matters to users. If the lingo that your users use outside of the API is very similar to what they use in the functions and methods, etc., for the API, then it will be easier, the cognitive load, the demand that the API puts on your brain will be lower. So closeness of mapping is very important to consider in terms of API. What are the words we're using? And are we using the words in the same way that are typically used outside of program? Then, consistency. Consistency is also not a very hard property to talk about. It means that similar constructs in the language have the same notation. For example, in textual programming languages, if you create a function, then this function visually looks the same as built-in functions. Maybe you've never thought about this before, but in Python, for example, you have a print method. And if I create my own method called is it sunny today, the interface is the same. It is from the call side. It is both the function name, brackets, potentially arguments. It doesn't matter if this is print or is it sunny today. That is nice, of course. You want similar things, functions, to have similar behavior because that makes it way easier for the user to use stuff in a proper way. And I said this early in the talk as well, APIs are sometimes designed with, oh, let's expose this and add this, oh, and a little bit of this. One of the things that sometimes suffers there is consistency. Because halfway you might change your mind and like, oh, no, we do it like this. Consistency, or let's say inconsistency, is a big source of errors. So then, the final dimension is provisionality. Provisionality is the ability to try things out, to sketch. So does a language allow you to make a half program, to try some things and to see if it works? Or do you have to get like everything correct in one go? So again, final dimension, final panda, think a bit. What are features of programming languages that help provisionality, that make it easier for you to try out things? An example of something that actually hinders provisionality, so that makes it harder to try stuff out, is a type system. So maybe you thought of this as well, is that, oh, it really helps me for sketching if there's not a type system. Because if there is a type system, you have to do more work. You can't just throw a few things together because the types have to match. Or rather, if you're using something with types, it's like, oh, first I have to create something of this type, but I don't know if this is the right type, and now I have to work with it. Oh no, it doesn't work this. Oh no, this is these things don't work together. So a type system is something that's typically set to hinder provisionality a bit, to make it harder to try stuff out. This is definitely a reason that some people don't like type systems at all, because they're like, no, I feel like I'm fighting with the compiler all the time. I just want to like get my thoughts on paper, get my thoughts in programming, and then I just want to have it checked later. So it's interesting because here we're saying provisionality is hindered by a type system. While earlier we said, well, error proneness is actually improved by a type system. So you see that many aspects that programming languages can have aren't the one or the other. It's never like, oh, if we would only have this dimension set to maximum, everything would be flowery and perfect. This is why the framework, as I said early on, is also called dimensions, because they sort of stretch, right? You take one and you move it a little bit here, and then the other one is attached and goes a little bit there. So if you turn the knob, which the cognitive dimensions framework calls a design maneuver, if you turn the knob on error proneness, your language might be less prone to errors, but then it also might have less provisionality. To wrap this all up, I know it was like lots of information, lots of dimensions thrown at you. Clearly, if you read my book, there are more examples and it goes at a slower pace. But I hope the sense that you got, the things you take away from this talk, is that cognitive dimensions can act as a checklist. You can look at all the dimensions and say, okay, so our library, how is it doing on consistency? Are all our features the same? And like, yeah, most of the things, yes, we're happy with consistency. What else? So what about viscosity? Is it hard to change something? Let's try to change this one call into a related call. Is that a lot of work? Oh no, that's okay. So you can really tick off all the dimensions. And it's not so much, as I said, to score yourself to, oh, wow, well, you're 7 error prone. It's much more that if you're designing something for people for their best cognitive understanding, it's just good if you have at least thought about all those dimensions. And when this is especially useful is to evaluate changes. So it's very hard to say how is our viscosity now at this point, or how hard is it to change something. But if a new feature is added, a new function, a new method, a new object, then you can say, this new feature, how will this impact the viscosity? How will this impact the error proneness? So changing something, making a change to the language is a great moment to start checking the checklist of cognitive dimensions and to see what does this new function do on, and then all of the dimensions. So that's it. That's everything I wanted to share with you today. If you want to know more about this, clearly something that you could do is read my book, The Programmer's Brain, that has all sorts of information on exactly this. How do we help the brains of programmers? So what I covered today was a bit towards the end of the book. And in the end of the book, we talk more about working together. So creating an API for others to use. Earlier in the book, we talk more about how to strengthen your own individual memory, how to learn new programming languages more effectively, how to read code better. But everything in my book is really centered about the unique cognitive challenges that being a programmer brings. That's it. That's everything. If you want to follow more of my work, I'm on Twitter under @Felienne, and my website is felienne.com. And if you go straight to felienne.com/book, then you can pre-order the book straight away. The ebook is already available in full, so you can buy it and start a reading straight away. And the print book will be shipped after the summer, so it is almost ready. It's really like going to the printer one of these days. One more thing, if you liked listening to me, you might also want to check out my podcast. I'm one of the hosts of the Software Engineering Radio podcast, a weekly interview format where we interview all sorts of software engineering professionals about a broad range of topics. So going from like Kubernetes and databases to also soft skills that are relevant to software engineering professionals like interviewing or writing documentation. That's it. Thank you very much for listening, and I hope you enjoy the rest of the conference today.